This is the Amp Hour Podcast, recorded May 4th, 2016, episode 297, an interview with Jake Baker.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Jake Baker.
Welcome, Jake. That's a heck of a title you got there, Jake Baker.
That's it.
We have intrigue and mystery. So, Jake, what is your main profession?
So, I'm a professor here in the U.S., and I've been a professor at University of Nevada, Las Vegas, where I am right now, University of Idaho, and Boise State University.
Awesome.
Why Las Vegas? Is that where you grew up? Is that other things brought you to Las Vegas? It just seems like it's in the middle of nowhere.
I have needs.
Right.
No, I went to high school here, and when I finished high school, I had one option, and that was to go to UNLV. And then after I'd been working for 27 years, I guess, my kids are grown. I wanted to go back and give back to my alma mater. So I was going to come back for a sabbatical. They offered me a job instead, and here I am.
Well, that's awesome. And so we should get to the meaty part. What is it that you teach? This is the part that professors are interesting. I think the stuff you teach is even more interesting, though.
I teach basically chip design, and I'm a little bit different in my courses in that I also have courses in how to design like memory circuits, which is a topic, as far as I know, not really taught at the university. So I've got classes in memory circuits, mixed signal design, advanced analog, and digital IC design, but more from a physical point of view.
So it sounds like all of this stuff that we pretend to know what we're talking about all the time, Jake actually knows what he's talking about here. So,
excellent.
Yeah, that's crazy.
Is there much call for chip design these days? Is it booming? Is it
busting?
Busting? What's going on? What's the vibe?
We do see a lot of news stories about, fabs closing down or, like Intel just closed that thing like we talked about it last week, and other, chip design going over to Asia as well. What is the main feeling there?
So it's a little bit complicated question to answer.
Of course, that's why I asked
it. There's still lots of chip jobs. There's a lot of the jobs have moved overseas to Taiwan and to China. There's still big companies here, Qualcomm, Broadcom, Intel, Micron, that are doing chip design that hire people with semiconductor skills. The big difference between now and, say, 20 plus years ago is that nowadays it's really hard to do a chip design from scratch. Yeah. Everything is evolving, and so it's not as glamorous as it used to be.
Right.
Well, I'd like to hear about the glamorous old days if you don't mind taking us back a bit.
Well, you lean over a bench and you've got these big vellum films and you've got a magnifying glass.
Knife.
Yeah, exactly. It used to be that you would attempt new products. If you had an idea, the company might back you and you would do a brand new chip design. And, nowadays the market and the companies have gotten so risk averse that it's really difficult to do anything that's totally new. Everything's just small baby steps or changes from existing products. And part of the reason is nowadays the reticles, the masks that are used to make the chips are just so expensive that it could sink a company if the company invests in something and it doesn't end up making a product.
Could you give us a scale reference for that? Like, what's a reticle set these days?
Millions, tens of millions, if not more. For the little ones, and
for a small analog chip or something like?
Oh no. There's companies like On Semiconductor is a great example, and there's others. that have a business model of not advancing to the newer technologies,
Right.
but rather providing technologies for medical and automotive and parts that don't need to have billions of transistors.
Yep.
Right. Yeah. Like stay on that old node, use the old equipment, stay on
Yeah.
8-inch wafer instead of 12-inch, all that
Well,
kind
you
of
could
stuff, right?
argue that there's greater margin potentially in niche stuff like that.
Yeah,
Niche
because
stuff.
they need to fab it, and they can charge a little bit more. They can focus on increasing yield, which increases profits. And if they have a piece of equipment that goes down, it's easy to replace. Find some surplus equipment from one of the big guys.
Right.
Not always, though. I recall stories of them buying, $10,000 desktop computers because they had to match exactly in fabs. I've heard those stories before too. The copy exact stuff.
Yeah, one of the guys I know of, my friend that's in a fab, he says there's the golden rule in fabs is there's no trivial process change, nothing. Even you get a different cable, you got to get the same one.
Yep, exactly. Exactly. Right, and people take advantage, sadly.
Oh yeah.
So you mentioned the golden days 20 years ago. Could you give us an idea also on? Dave was asking about analog versus mixed signal. But you also mentioned like the billions of transistor type stuff. Where did that all fall back then? I mean, was it like were you doing entirely new architectures as well, or is it more subsystems within a larger chip?
So, for example, in DRAM memory design in the 90s, you might have two design engineers that design the entire chip.
Wow.
Big cost was in the process development, so it was done at the same time as the designs. And so these chips would sell hundreds of millions, if not billions of dollars worth. And so the engineers were, I say glamour, but I mean, they were making ridiculous amounts of money. And then as things matured, companies fell out. We went through hard times.
There was the price fixing scandals.
Yeah, exactly. There's all kinds of things. Then, what you could do in designs, and your responsibility tended to be a smaller and smaller part of the project.
I see. So it just became more of a business, basically, like less of a design R&D focused organization, more of a accounting driven type thing.
To some extent, and the other extent, frankly, the personnel costs got to be almost negligible compared to the other costs. And so from point of view of someone running $1 billion company, it's easier to throw people at something so that somebody leaves, there's still people around to pick up the slack.
Yeah, that makes sense. Well, we could try to go through some of your patents if only we had the time. I don't know if we've had someone with this many patents on their show. What is it, like 180 now?
No, it's
142.
142,
yeah.
Sorry. I didn't have the page right up there.
And how many of those actually get granted? Or like what sort of percentage of them?
Well, okay, so this is interesting because when you look at the number of patents, you go, wow, that's a lot of patents. But in reality, it's not as many as it appears. And here's why. When, say I do a patent on some double data rate DRAM, which I did in the 90s, and there's 20 claims of the patent, and the Patent and Trademark Office will issue 10 of the claims.
Right.
Well, what will happen is the attorneys will turn around and take the other 10 claims that weren't issued, and they'll file a continuation, which has the same title as the previous patent, but they'll change the spec or the claims in such a way to get around the objections of the Patent and Trademark Office. And you keep doing that. And if you look at the titles, it runs up the number. So I have 142, but maybe 50 of them are different ideas.
Right. Got it.
So it looks more impressive than it really is.
Is this a driver? Is this something that you do for the university? Is this something that they require, that you keep churning out patents like this? Is it sort of expected?
No. Well, they expect it if they like it. If they're the assignee, they're the ones that own the patents. But almost all of my patents are as a result of consulting work I did in industry.
Oh, okay, right.
So the university,
So they're yours.
No. They're the company.
Oh, Dave, easy there, buddy.
It would be nice.
Yeah.
No, they're the companies.
They're the companies, right? So the companies pay for them because you're probably like you couldn't, as an individual, you couldn't afford to just patent everything like this.
Well,
you have to pay for all the development too, right? I mean, that's
sometimes people will file patents without doing any development and showing that the concept works. The thing is, with a patent, especially in semiconductors, it's only worth something if someone will license it from you, and a lot of times then you have to go back and get into litigation or go after a company and
Has that ever happened? Have you ever had patent wars? Have you ever been involved in them?
Well, I mean, I've done lots of expert witness work, so yes. I haven't done any with regard to my patents. A lot of my patents are in double data rate stuff, and so when DDR was coming on from SDRAMs in the late 90s, I was still working at Micron, so I wouldn't have been involved other than I've been deposed as a fact witness. The later work is done in resistive memories, which are like the 3D crosspoint switch stuff that Intel and Micron are talking about and others. And there's really not a lot of players in that, and I did the work for the people that did the product, so I don't anticipate there being anything there either.
That is interesting too, that it seems like, I mean, just the overall number of players is going down too, right? As these companies get bigger and bigger, there's just fewer. I mean, they're obviously, there is the bigger piece, they're bigger companies with more lawyers, but there's a lot fewer of them. They probably trade patents as much as litigate type of stuff.
Yeah, what happens now is, especially in downturns or when a company goes out of business, they'll go to a venture capital company with their patent portfolio and say, save us. And in order for the VC firm to make money, they take the patents and then they'll go after, sometimes legitimately, sometimes not. They'll go after people that are making stuff.
So we're going to talk about Rambus now? Is that what we're going to talk about?
Well, yeah, I haven't kept up on them since the 90s. So
Me neither. The only reason they're still in the foreground of my mind is that I still recall with hatred in my heart that I had this top-of-the-line computer with RDRAM in it, whatever that stood for, I guess Rambus DRAM. Yeah. And I remember all my friends were buying this cheap DDR memory, and I was stuck with like $500 memory modules, and I'm like, I can never update this computer. It was basically obsolete. It was cheaper for me to just buy a new computer. It was crazy.
Oh,
yeah. I do recall it, but I don't recall the technical details. Why was it so much more expensive than
Rambus.
DDR?
Yeah.
Why? Because they charged a premium because they had patents on it, or what? What was the...
I
why
think
was it more expensive?
I think that's part of it. They, put the toll on any of the memory makers that were making the parts.
Right.
And at the time, the parts were not synchronous, and so there was a delay between requesting something and getting it, and so it really slowed down the performance. And in Rambus, everything was, very synchronous and quick, and so the performance initially was better.
I see.
Okay.
And then like the bottom up type, they started fixing it in other ways. Basically, that's kind of the idea.
Yeah, went to a wider bus with the DDR and increased the latency, the number of clock cycles to get something out of the part, so that once you got over that, you get stuff out really fast, and a bunch of other things that weren't common in the time before that.
So how did you get into RAM in the first place? I mean, how did you get into this side of the design field?
Oh, so I in the 80s, during Reagan's Star Wars program, the Strategic Defense Initiative.
Yes.
Oh, yeah. Chris, can we insert sound of a flushing toilet?
Yeah, right. Laser blaster sounds or something? Or?
No, flushing
or do you mean like Reagan
where
clips
or
something?
Like,
Well, it's good for people working.
Oh, yeah, I know.
Anyway, I got hired to do design for instrumentation at the Nevada test site, so I'd go out there for the nuclear bomb blasts and all that, and that lasted, I worked there from 85 to the early 90s, and then there was a moratorium on nuclear weapons testing, and I had been teaching part-time at UNLV, and I really liked it, and I decided I'd go back to school. And anyway, long story short, I got a job in Boise, Idaho, and there was the company Micron was there, and part of what they encouraged me to do is build relationships with Micron, and that's what I did, and that's how I got into all the RAM stuff.
Got it.
Wow. That's great.
How does DDR work for those who aren't familiar with the concept? And what's the differences between DDR 1, 2, 3, all that sort of jazz?
Yep. So the initial DRAMs, basically you had what's called a RAS, a row address strobe, which you also have in the DDR parts, but it's more of a control signal. It doesn't do the same thing. And you have a CAS, column address strobe. In the older parts, you would multiplex the addressing into the parts. So you'd strobe in a row address, and then you'd strobe in a column address, and then you would wait a while for the part to produce the data on the output, and then you would read it in. Why did you have
to wait a while?
Well, because it takes time to open the row that you select, and then it takes time to sense what the value of the data is, and then it takes time, once it's sensed, to feed it from the array, because these are big chips, to the output of the chip. Mm-hmm. And then there's the time of flight from the chip to the memory controller.
Right, so it's a propagation delay thing. Yeah. It's not...
Yeah.
Right,
yeah,
just because the silicon's so physically large.
Yeah, and then when they started doing things with synchronous DRAMs, what they said instead was that we're going to send in data with this clock, this COK clock. We're going to do everything on the rising and the falling edge. Well, for the commands are on the rising, but the data is going to come out on both the rising and the falling edge. And then because the delays are so long in doing each one of these operations, what we're going to do is we're going to add this latency or delay of a number of clock cycles. So in the earlier DDR parts, like DDR1, there might have been 1 or 2 clock cycles between issuing a command and then getting a chunk of data out. And then, but after that 2 clock cycle delay, the pipeline was filled and you just get the data out as fast as possible. Well, all these, and it's interesting to note that in all of the DRAMs, DDR1, synchronous, extended data out, all the older ones, DDR4, the memory, the DRAM memory cell, sensamp, column decoders, all that organization is exactly the same. I mean, the process technology has changed. All they've done is they've changed the wrapper around the memory. And so you would get like 20 clock cycles of latency, and now you can get stuff out at a gigabit because you ensure that any one hop is less than, say, a nanosecond.
Yeah, that's crazy.
Yeah.
But yeah, you're right. The everything else is. I remember sensamp stuff was very basic for. I used to work at Samsung on memory stuff, and we learned about the sensamp first, and they're like, yeah, this is pretty much. Pretty simple. You just go with it,
Yeah, it's just 2 inverters back to back, and then everything is in the process to try to optimize it, reduce the offset, and improve the yield. Yep. So that improves the signal-to-noise ratio.
And the yield increases the money coming in.
Yeah, exactly. More jelly beans.
So all the smart stuff is in the process, right? It's not necessarily in the schematic implementation of how you implement and architecture.
Going the other extreme. No. If you look at like flash and DRAM to a certain extent nowadays, they do so many things with like trying to wear level so you don't wear out the cells. So the software part is huge. Right. In DRAM, it's all about speed. And so the difficulty comes in they have all these algorithms for like measuring the distance the DRAM is from a controller so you can optimize the timing window and all these other things they do that maximize the performance.
Yeah. Crazy. That's interesting too, because it kind of, I remember it was maybe it's out of my purview these days, but like it was such a big deal for computers and everything. Like buying memory modules, and it feels like everybody's kind of moved on to tablets and laptops and stuff like that. So it's almost like it's just built in now. You know what I mean? It's just you hope for the best stuff, and it's built in. Whereas it used to be like people optimizing memory sticks on their desktop type stuff. So, and I'm sure gamers still do that, but.
Now they're trying to go to the hybrid memory cube for the DRAM, where they're putting through silicon vias through the chips and then stacking them, and then putting the cubes around the memory controller. So
that's crazy.
Yeah, little sugar cubes.
So, aside from DRAM, what are some of the other types of circuits you've worked on in the past?
Well, when I did the Star Wars stuff, I did all kinds of high voltage and cameras and all this for recording the the bombs going off. But consumer electronics, I've worked on like CMOS imagers, for example.
Oh, wow.
Micron acquired a company called Photobit, which was out of Caltech in the when was that? Late 90s. And I went down there and I helped transition the products into the Micron fabs. And the idea there was to use the old DRAM processes to run the CMOS imagers because they could be larger for obvious reasons, to collect light. And then I've worked on flash. I've done quite a bit of flash memory. And then I've done quite a bit of resistive memory development, which is everybody says is going to be the new flash replacement and hard disks and mass storage because they can stack it. And
could you explain what that is a little bit more?
Please.
That's not like the what's that
Tell us
fourth
why.
element? It's supposed to be the
the memristor.
it's not that,
yes.
right?
Some would argue you could say it is or whatever, but I worked on it about 10 years before I heard the term memristor. So,
Okay.
So someone with clever branding know-how got in there.
well, I think the guy is a professor at Berkeley. He coined that term. What's his name? Leon Chua. In the early 70s or sometime around there. Anyway, no one realized he'd already discussed this potential element, just he hadn't fabricated it. Anyway, the resistive memory is, in simple terms, it's just a memory that you sense the resistance changing. So a program state might be a small resistance and an erase state would be a large resistance.
Oh, interesting.
Yes.
So is it like lots of instrumentation amps, or how is it actually measured then? Or is it just current flow changes?
So imagine a screen, just like on your window, a window screen, and at the intersection of every intersection of the horizontal and vertical lines is a memristor. And then they put a material in there that behaves like a diode. So you have a diode in series with a variable resistor. And then depending on how you apply potentials to the elements of the screen, and the rows would be the horizontal wires and the columns would be the vertical wires, you can then select a row of memory and then apply a small voltage below the diode turn on to sense how much current flows, and then thus what's the state of the memory cell.
I thought you were going to go into like the infinite array of 1 ohm resistors or something there. I started to have flashbacks. Sorry. It's always a threat with professors,
Yeah, I'm not a very theoretical dude.
Oh man, that's funny. Yeah, no, that's really interesting. And so this is actually coming on. I've never heard of this stuff before, but that doesn't mean much. Where this is kind of starting to come online with larger memory makers, or what?
Yeah, Intel and Micron a while back, a month or two, just announced a press release that they were going to start releasing samples, and it's going to be. I think everybody in the industry feels that this is going to replace flash memory. When it'll actually, you'll start seeing it in your laptops or computers or servers or whatever. I have no idea, because they were talking about this, like I said, back in the mid 2000s, and I worked on it for a very long time.
What is the advantage of it? Why is it going to replace flash? Is it faster? Is it cheaper? Is it denser? Is it all of the above?
All of them. All of them. It's
All right, this is good.
So the problem with flash is that I don't know how well you know it or the listeners know it, but there's a tunnel oxide, and you have to apply a large voltage to the flash cell to get tunneling through this thin oxide, and it damages the oxide, and then there's physical limitations on how, because of the material properties, how thin you can make it. And so it limits the size of the memory cell. And back in 2008 or 2007, 2008, I was working on 35 nanometer flash. I would guess nowadays they're probably in the like 10 nanometer flash range,
Insane.
Which is just, blows my mind. Because
usually they're chasing leading process stuff, and
yeah.
So yeah.
Yeah. So
how does the damage happen? Does it happen on every write, or is it more a bit random? Is it quantum-y? Is it what's... That's a new word. Shush.
Dude, it's tunneling, Dave. Come on, man. It's like a worm.
Yeah, but like,
Electro worms.
Yeah. My understanding is that when you apply the high voltage, it damages the materials because you have the carriers, say electrons tunneling through onto a floating gate. And when the carriers tunnel through, they can do damage as they're moving through the materials.
So it's every write? Every write does a small bit of damage? I thought that the scale is already so small that if you did damage writing every single time, wouldn't last millions, it'd last
These are small
hundreds.
gates, Dave.
Yeah, it does. The older flash, they had the spec of you could write to it like 10,000 times.
Right,
I don't know what the exact spec is now, probably hundreds or maybe 1,000 if we're lucky. But yeah, it's funny because I mentioned before we started recording that I just installed a solid state drive on my laptop. And one of the things that I mentally did after I installed that was turned off my disk defragmenter. So that it wouldn't go in and readjust anything,
Right. Yeah, it's like needless reshuffling. It's like, I can't afford that.
No, it'll wear it out faster, right?
Right.
Yep.
It's weird thinking about solid state drives like tennis shoes now.
Yeah, exactly. Yeah.
Well, Dave's had that problem recently, right? Right, Dave? You've had some bad drives.
No, it turned out to be the cable.
Oh, well, there you go, too.
Yep. Cable was dodgy. Everyone, like I put it on Twitter and everyone said, oh, yes, solid-state drives suck. It's like, well, it's the first time I've heard of it. And they're saying, oh, all these brands suck. And no, you've got to get Intel, blah, blah, blah. And no, it turned out to be the cable. There was nothing wrong with my drive.
Oh.
So.
Yeah. So I was mentioning that about the time, I don't know when the resistive memory is coming into market, and I've been working on 10 years. One of the other products that I worked on back early in the 90s before LCD displays came into is called a field emitting display. And it was going to be a CRT replacement. I don't know if you've ever whacked open a viewfinder in an older camcorder and you see this
Yes, I have.
Yeah, 3-inch little CRT, right?
They're great.
Yeah.
They're so sexy.
Yeah. So anyway, we worked on that, and this is when I learned. I was like really excited. I designed the field emitting driver. It was on a team. We were working. We demoed the product and all this, and I was thinking, man, we're gonna this is gonna be great. We're gonna
take it over the market.
This was before LCDs were blowing up the market, right?
Yeah.
And it turns out that we could get like 99% yield on the pixels in the array, but that 1% your eye could pick up, and that's when I learned you need having ideas and turning them into product is really really challenging.
Yeah. Right.
I can remember back when LCDs were starting to take off, and it was actually normal and expected to have dead pixels on your brand new laptop. They would actually say 10 dead pixels normal. You cannot claim that under warranty, and people like, oh yeah, okay, there's a few dead pixels, and your eye would pick out one dead pixel. It'd be so obvious,
Yeah.
And that was normal. People treated that as, okay.
So what happened to the field? So field emitting displays are different than CRTs. They're not. Are they like still reversed, like electron shot at a phosphor type thing?
Yeah, that's exactly what they are. There's we did it in like 5 micron NMOS, so it was real old technology, again, with the idea that we keep the costs low by using older equipment. We would etch a field emitting tip down into the silicon wafer, and then you would put a layer of glass and phosphor on top with a metal grid right above the tip, and it would extract the electrons off the tip and hit the phosphor, and that's how you'd get the red, green, and blue.
Wow.
Sweet.
So it was like basically a miniaturization of CRT stuff, huh?
Yeah, miniaturization, making it flat and using silicon.
Wow. That's interesting. Well, why didn't it take off? Just because of power and cost, or what?
No, it was we just couldn't get the yield up to a level where it would be manufactured. It'd be like we would get like 99% of the pixels working. They'd last indefinitely, but there'd always be dead pixels in there.
I see.
And it was, the size of those displays in the camcorders were relatively small. They're like VGA size, and so having a few dead pixels really.
It stands out.
Yeah, especially when they die in their bright spots. If they died and were black, it might be less noticeable.
Yep.
Oh, interesting. Wow. That's really that's really cool though. That it's just crazy how that kind of stuff. It's a mostly viable technology, and yet it just got passed by because of an alternative technology.
Yeah.
It's crazy.
Yeah,
and you couldn't quite perfect it.
Yeah. Yeah.
There's probably a ton of tech out there like that never made it because it was almost that last hurdle.
Yeah.
You know, they just couldn't get over it.
Yeah. Yeah. It's lessons learned about product development. And I think nowadays that's one of the reasons they're so risk averse in trying new things.
Right.
So.
Yep. Yeah, just more competition and cost to start up and everything too.
Yeah.
So.
Yeah.
So what is the so are you still designing chips? Is that I mean, I know you're teaching and we're going to get into that in a minute here, but are you still designing and consulting for design?
I'm still designing chips. I'm doing a lot of work with the military, designing like sensing chips. I'm not designing in the newer technologies just because keeping the CAD tools up and running is painful.
Oh, yeah.
And I have to do a lot of that myself. And so I tend to steer towards the older technologies. I do a lot of consulting with expert witness work now. I'm trying to focus on some, and maybe we'll talk about this later, but I really have a passion for online education, and I'm working on university courses that will be online that the students can take that are that they like.
Awesome. On what platform are you going to release those?
What I'm going to do, so this is still in a state of flux, but I want to do like basic circuits 1 and circuits 2, and I want to have it so that it's web-based where the students will have like mini lectures. Right now I'm thinking like 15-minute lectures over topics that I'll do recorded examples working. Then they'll have like an online quiz that they take, and then periodically some online tests. And then I want it to be clear, and I want it to be no hocus pocus, because I get students that come in and they just, they don't understand simple things like dBs and why a log plot is used and all these things that are just not difficult concepts, or an op amp. Students come in, they're like, oh, I took circuits 1 and circuits 2 and an op amp's magic. And then I spend 15 minutes and I go, this is the way it works. And they're going, what? It's that easy? Yeah. So
is this going to be your own developed web platform, or you're going to use like a existing technology web thing to like share it and do all that sort of stuff?
Well, right now I've got a bunch of videos on my website, the CMOS Edu website. The university here, UNLV, has indicated they want to work with me, so they're going to give me a PHP programmer to help develop.
Oh, okay, right. So it's going to be a custom thing, right?
Yeah.
Got it.
And I'm going to have like different, in order that two students aren't sitting side by side and working together, I'll just have some randomized problems so they get different problems and a bunch of other things. But I think I have this vision. We'll see how it goes.
Got it.
So so you said you are still designing though. What kind of nodes are you on then? I mean, so I think we've talked to someone else about that with like the process kits. Like you mentioned the super expensive keeping up with cadence and for like the 20 nanometer stuff or whatever's the newest. What nodes are you designing on?
Right now, the smallest we're doing is old 130 nanometer SiGe, silicon germanium, because we can do a multi-project wafer through the Moses service, which is where everybody puts their designs on one wafer in fabs to keep the cost down. So. Can
you tell us more about that? We've actually mentioned that on here before. We've talked about it before, but never really actually going through with it. So.
Oh, okay.
How much does it cost? Tell us the price, son.
Yeah.
Okay. So funny you mentioned that. So a little history about the Moses service. It's MOSIS, which stands for Metal Oxide Semiconductor Implementation Service, and they started in like 1981, I believe, and they're out of USC's Information Sciences Institute. And they used to be funded by DARPA. Now they're self-sufficient, and they're self-sufficient in what they do to universities that want to fabricate, like me, is if you're teaching how to do chip design in your class, they give you free fabrication support for that class.
Nice.
Oh, wow.
Today, they give you 5 chips and they package them in a DIP 40 for student projects. And they're great for like lab stuff, doing inverters or some ALU or an op amp or measure resistance and all that. But I just got about 10 chips or 10 projects in the mail today for my students from last semester. Now, if you have funded research, then they charge you, and it's like for a 2.5 millimeter by 2.5 millimeter and like half micron older technology, it's like $6,000
for a single chip. Right?
Well, they give you 40 dice.
Oh, well, that's not bad.
So,
no, it's cheap.
Do they just give you the dice, or do they package them for you if they want?
If you want package, you have to pay extra. We actually just over the Christmas break, we have 2 wire bonders, and we wanted to develop wire bonding to the printed circuit boards here so that we could
nice.
Keep things down.
I was going to say, most people would choose the dip option or any package option, just anything but dice. Thank you.
Yeah.
I don't know though, because then you start adding. I mean, dips are not exactly optimal for adding in inductance and capacitance, all the other. I mean, I guess you can account for them.
Who cares? I mean, wire bonding.
Yeah,
pain in the arse. Your average person doesn't have wire bonding experience or the machine to do it, or.
Yeah, we have like test structures, and so one of the big reasons we do the wire bonding to the printed circuit board is so we can just rip off the wire bonds and wire bond over a new test structure to do measurements.
Ah, nice.
So it makes it easy.
Yeah, more swappable versus if you put it in the packaging, then you can't get at all the tags you're talking about.
Yeah, if you have like a avalanche photodiode in the middle of the die, and you have other circuitry around, if you bond out the other circuitry, you'll never have access to the APD in the middle. So
gotcha.
This way you can do all kinds of testing.
You see, Dave? No, that's cool.
Can Joe Blogs in their garage, who's willing to fork out $6,000 or whatever, 6 or 10 grand or something, how easy is it to actually design your own chip? Are the tools free?
Well, to engage, you mean, Dave, or you mean the design process? You mean to engage Moses or to make the design?
Well, both. A, is it possible? And B, how much, what are the tools you use to do it?
So that's a good question. So if you try to do commercial tools, which if you're doing the real smaller designs, you have to use because the process design kits, the PDKs, are only set up for the commercial tools. It's really expensive.
As in the commercial tools, Cadence and whatnot.
Yeah.
Right.
Now, having said that, Cadence has a program where they will sell you time on their server, which makes it much, much more reasonable for someone that, say, was interested in doing a startup. So you run the tools on their server, they charge you per hour, and it makes it so you can do something. They set up the PDK for you, and so it's really reasonable. I have on my website, I have another set of tools which are called Electric VLSI. They're really nice, and they are free, and they run on any platform, Unix or Mac or Windows.
Yeah, they're Java-based, right?
Yeah, Java. And I've designed I used to just use electric only for research and Cadence, and I've probably designed, me and my students, I shouldn't say me, have designed more than 20 chips using the electric flow. The problem with that tool, I mean, it's a great tool. The issue is if you go to the smaller technologies, it doesn't have the PDK. So you're forced to go to Cadence. The other issue for me is someone that's trying to educate students and make them marketable and attractive to potential employers is they don't use electric in industry. They use Cadence.
Of course. Yep.
Right. Yeah. So I switched over a few years back to teaching Cadence only.
Oh, really? Okay. Interesting.
Yeah.
That makes sense. You can't.
We talked about electric in the past as well, as when we found out about it. What was it? 2-3 years ago, Dave? I mean, not like it's only 2-3 years old, but we talked about it on the show 2 or 3 years ago, and I was a little confused when I first opened it up, but at least the fact that it exists is nice.
I put some tutorials on the CMOS EDU website, some videos, and some written tutorials. So they're actually used a lot by everybody around the world. I didn't realize, but I went to, I got invited to give a talk in India a few years ago, and I went with some colleagues, and this was at a time when there were quite a few companies moving into India. They were looking to hire people, and I didn't realize how many people were using the videos and the tools to get this experience, and had got employment until I visited.
Wow, that's great. That's really great.
And you are the author of 2 books, are you not?
Yep.
Tell us.
There's 2 CMOS books. One's called CMOS Circuit Design, Layout, and Simulation. The other is CMOS Mixed Signal. I've got a 3rd book with my students called DRAM Circuit Design. That's in 2 editions. The Mixed Signal book's done 2 editions, and then the CMOS Circuit Design, Layout, and Simulation is done 3/4 editions, because the 2nd edition was revised, so there's a revised 2nd edition.
All right.
So yeah.
I see a Chinese edition of this CMOS circuit design. Is that is that something that the publisher did? There was a huge call for it in China to be translated into Chinese. What?
Yeah. So I think the Mixed Signal and the CMOS Circuit Design book were translated into Chinese, both traditional and simplified. The what they did, the publisher had an agreement with a company in China, and then what the company in China did was they took the book and they split it into 3 books so that it would, I guess, sell, and that made the Chinese that were purchasing it really upset. They were like, "Why did you do this? Why didn't you keep it as one book?" And so, anyway.
Oops. Yeah.
Is yours the go-to book in circuit design? What are the go-to books?
I think in digital there's several popular books. One is Westy and Harris. That's CMOS, VLSI, and they're heavier. And also Rabai has a digital integrated circuit book with a couple other co-authors, and at least the Westy book is more geared towards real digital design, like he has Verilog and VHDL, and in my book I'm more geared towards the physical process. I don't want to teach Verilog. We have that taught in other classes. I want them to know what the layouts do, and the difference between diffusion and depletion capacitance, or strong inversion, weak inversion. So I'm a lot more physical. Other books in analog are like Gray and Meyer and Hurst Lewis, the analysis and design, Razavi's design of analog integrated circuits. There's several other good books. So I don't know if I would say, mine's the one everybody goes to, but I like to think some people do.
Excellent.
Yeah.
We'll link to those down below.
So then on your page for this book too, you have, you link over to the electric stuff. Does that mean you use electric in the examples when you're talking about this thing, or do you have to tie in the software piece when you're teaching the actual circuit design? Is that a really integral piece? Nowadays, I like the students to be able to build stuff, to simulate things, and to really understand what's going on. And so when I was using electric, we did, me and my students did all of the examples from the book using electric. We did them from Cadence, and we did them in LT Spice where possible, and some other tools. Cool. Yeah, that's good. So what are the usual tripping points then when a student comes to you and is ready to learn some of the mixed signal stuff? Are you designing all the way down you're designing individual transistors? Is that kind of the idea? Yeah. So yeah, go ahead. I was just going to say so with basic circuits, like when they're learning analog, my pet peeve is you got to know RC circuits, and if they know second order circuits like RLC circuits, that's great. You need to know, like step response, phase margin, gain margin, what a Bode plot is, how to look at it and not cringe. Right. I'm still working on that one, Jake. And then for the mixed signal, it's really, and other people would argue with me about this, but I really feel the power of mixed signal design is the fact that it utilizes digital signal processing. And so having a very strong signals and systems background
and understanding what's happening, from a signals and systems point of view, and how you do the digital filtering, like in a delta sigma modulator, what's really happening there. Those fundamental circuits and signals and systems are really important.
So in those kind of designs, so using that example, right? So say you're using, like multi-tap filters and stuff like that.
Mm-hmm.
Would that be like you would design a front end analog piece, and then you would tell them to go code up the rest and generate do you generate the multi-tap stuff, or do you have to actually design that out and have each individual piece individually designed?
So
like what level is the whole design stack, I guess, because you talk about VLSI, or you talk about these Verilog versus VHDL stuff, but how much is the tool doing it? How much is the student doing it?
So I don't, in my classes, I briefly talk about Verilog, but like I said, they get in others. When like if you look at stocks and stock performance in the stock market, and you can apply like a 30-day filter or a 60-day filter or whatever, I want them to understand what's going on there, because it's not that hard. Once you understand what the filter is, what its frequency response looks like, how to modify it to get a band pass or a high pass response, physically what's happening, then we build circuits that utilize those things. And I don't do too much. When I say digital signal processing, a lot of times when people say that, or most times, I think people think of multiply and accumulate, like the tap, right? And that's not what I teach. I teach like taking the bilinear transfer function, implementing it digitally, take the biquadratic transfer function, implementing. How do you implement those digitally? What's going on? How do you make a higher order filter using those things? How do you implement those in silicon using transistors, and if you need adders or just delays or whatever. So it's a really low-level, hands-on kind of approach.
So when you say, when you meant digital signal processing, you mean making digital structures that are doing the processing on some kind of signal output versus using multiple iterations in a processing element.
Yeah, so when I say to the students, when we go through it and I say, we're going to use decimation, and I ask, how many of you have taken a DSP class? And they say, half the class raised their hand. I say, what is decimation? And their answer is, you throw out K-1 samples. Yeah, you just throw out some samples, and I'm like, no, you're down sampling. Whenever you sample, what do you have to do? And they're like staring at me, and like, you need an anti-aliasing filter. How do we implement that digitally before we decimate? Before we, it's kind of, it all makes sense now.
Right. Yeah, so it's like you're basically taking them, you're like magic school busing them around the actual silicon then.
Yeah. I guess that's one way of looking at it.
Yeah. That's crazy. Yeah, and so let's get back to kind of how you started the whole conversation too. I mean, what's the likelihood that it's very important to understand this stuff. What's the likelihood that someone that goes to work at a chip design company will actually be implementing these kind of structures at the silicon level?
Well, it could be quite high if you have that arsenal of skill, right? There's places where you can use it. I can give you an example. I worked on flash memory, as I mentioned. And in flash memory, the way it's read is you pre-charge a bit line, which is the column line. And then if the flash memory cell is erased, it discharges the bit line. And if it's programmed, it doesn't discharge. And so you put a comparator there, or more than one comparator, and you look at what happens to the bit line. That's how a flash memory works. Well, I had this idea that, it would be better if I use this delta sigma process to hold the bit line constant and measure the current that was flowing. And I could actually, and I implemented it with a counter, a simple digital filter, and I could actually plot the current that flows in the flash memory cell. And I was like really excited. This is going to be, huge product. We're going to make lots of money with this. This is going to revolutionize flash and all this. And, it just, because I had that arsenal there that I knew, I was able to do these things. And so when I educate, I'd like to think every educator thinks like this. You want to educate people because you don't know what the future presents them and what they'll need. You want them to be armed with,
Yeah, given a toolbox.
Yeah, given a
basically,
toolbox to solve stuff. I can't tell you how often around, and I'm sure you guys are in the same boat. You have something break around your home and you need to fix it. It's good to know how to fix it, right?
Right. Yeah, exactly. Or even I think a lot of it. So like that sounds like a very pattern matching type of thing. You understand the application, you understand the tools that are in your toolbox. You then applied that a different tool to it, right? So the Delta Sigma, like you said, and then you could implement this, which is quite an innovation then too, right? I mean, that actually does bump you forward in terms of what you can do with it. So that's really good.
It was really exciting. That's another example of learning about what actually makes into product.
Half of the art there is knowing which tool to use.
Yep.
Yes, definitely.
That's the finer art.
It's seeing it and recognizing it, and then pattern matching. I mean, that's definitely that's a huge piece. But I think you're right. If you're super focused on just the tweaking stuff, like you said, a lot of the companies are these days. It's more like how can we get these incremental benefits versus how can we change the paradigm? How can we change how we're actually doing things? That's a lot scarier for a lot of companies, I think.
Well, and to from their point of view, it could break a lot of companies if they invest $100 million in something and it doesn't work out. So
right. Yeah, it might be easier to just kick the can down the road, make the process a little smaller. I think it'll be interesting as they continue to run out of room, right? I mean, like, what happens then? Can you answer that question? What happens?
Is Moore's Law's dead? First of all, everyone's saying, yep, it's basically gone, as we know it.
Well, I think from they, instead of increasing the area or reducing the size, they're doing what they're doing. They're going to start going to stacking the chips. It's just like a densely populated area once you run out of...
But once you decide to do that, Moore's Law is dead. It doesn't apply anymore.
No, then you go up, Dave.
Yeah, but it doesn't apply because Moore's Law applies on a two-dimensional plane. It does not apply to three-dimensional stacking.
Yeah.
Surely.
So, I think the same way with what you're saying, but when you talk, say, in a memory and you look at the size of a memory cell or the size of a transistor, whatever, and you say, okay, the pitch, which is the like distance between points, is 2f, and then the pitch in the other way is 2f, and so the size of the memory cell is 4f squared. And then they start stacking them, and they go, look, I put 4 planes here. I've got a 1f squared memory cell. Look how I'm...
Right. Yep. It depends on how you look at it. Do you look at Moore's Law from a photographic, process kind of thing of shrinking things down and doubling, or do you look at it as a macro thing? Okay, memory's getting, half the price every and twice as much every, 9 months or every 18 months.
Mm-hmm.
And in that case, it can still hold, right? Because you just stack them.
Yep.
I guess. So. No, I was talking about Moore's Law in terms of, the actual feature size, the physical feature size.
Well, they did that, the FinFET stuff where they, again, went vertical and then the poly went over and then they can shrink it down a little. Physically, it has to end because
exactly.
You got the
I know.
So they're just, coming up with different ways to say, no, we're really cheating or we're really getting this enhanced performance. It's all marketing, to be honest with you.
Right. Moore's Law's just turned into marketing. Okay.
Yeah. We're in this advanced process and look how small. We're right on Moore,
Moore's Law, sponsored by Intel.
Yeah.
The three-dimensional silicon company.
Right.
Yeah.
What about, so a student getting started on this stuff, I mean, what is the path in, just even at UNLV, at what point in their journey are they getting to your class?
Well, as I mentioned a moment ago, I'm hoping they get to it in their second year when I teach circuits, but generally it's been senior. The chip design stuff is senior/grad.
Is it a compulsory part of the engineering course, or is it a optional thing?
Nope, they can select that, or they could go to power or whatever.
Right, okay. How
That's
many
great.
people are doing what these days?
There's quite a few people that want the power track because there's lots of jobs in power.
I was going to say, and it's probably easier, right? Where, your stuff is fundamentally, people probably, rightly or wrongly, people see it as difficult.
Yeah,
I would
yeah.
think.
I think that's what the students would say.
Right.
I think kind of lacking glamour, but
It is lacking glamour, yes. I can remember back when I was doing it, we had a power guy come in and it was practically pleading for people to come into the power industry. It's, I know it's not glamorous, but
money.
But we need people,
yeah.
hands and knees begging. Sad sight.
So where do you see? Okay, so you've seen a lot of the industry. You've seen you told us that Moore's law is going to end, if not soon, at some point. It's fine. Where do you see all this stuff going? I mean, are you gonna do you see the education piece still being able to expand to these lower nodes? I mean, how much changes when you go to the lower nodes, or where do you see even the chip industry going?
So I think it's tough to teach someone about the smaller technology nodes because there's just so many things that impede the learning process. Like, you can't turn it this way, you can't do this, and it's not really related. You got to keep them on a Manhattan style. So I think in the older technologies, and it might be sounding like somebody that teaches vacuum tubes, I don't know. But I think you can learn the fundamentals. I actually think you can learn fundamentals with vacuum tubes as well. You just can't do chip layout with vacuum tubes. You can still teach the fundamentals. I think that the future is going to be designing cells or modules for products where they're system on a chip. Well, I mean, future, it's the way it is now. And, you'll be part of a design team that does something, and you'll focus a lot on optimizing the design and looking at the trade-offs and ensuring that it's functions given, this happening or that happening or this yield shift or whatever. So.
Gotcha. Interesting.
What do you think about the Intel laying off, what was it, how many percent, 10, 12% of their workforce or something? Was that, okay, that's obvious, like, do they think they're going in, do you think they're going in the wrong direction or they missed the boat?
Well, first off, as someone that's been through working at companies, I was at EG&G when they had the nuclear moratorium and they had layoffs, and we had 3 or 4 rounds before I left and went back to school. And then I've worked in the semiconductor industry, and it's cyclic, and there are layoffs regularly there. When I think of that, I just think it's really hard being in that atmosphere because it's depressing to be around people that are worried about. And I mean, you may be worried yourself. I know that it's not fun if you're worried about losing your job. It's not a fun environment to be in. So that's what I basically think about when I hear about those things about how unpleasant the atmosphere is to work in, unless you don't care. Right. But as far as the if it was a strategic thing. I don't really know too much about it. If they had a fab they were closing and they had to lay the people off, or they were shifting focus, and
they can their Atom CPU, I believe.
Yeah. It's funny because I'm scratching my head. I read that news and I'm scratching my head a little bit because if you look at the IEEE Spectrum a month or two before they announced the layoffs, there were literally pages and pages of jobs at Intel.
Oh, really?
Yeah.
Interesting.
It was like literally hundreds and hundreds of jobs. And I told my students, I said, I just got the IEEE Spectrum, and there were all kinds of jobs at Intel,
Quick, take my course, I told you. It's great. And then...
Well, but you never know. They may be hiring in different locations, and the people they laid off didn't want to go or whatever. You don't know.
Right. And what about the consolidation in the industry? It's like we could almost do in every second episode, we can have news of another semiconductor merger.
Yeah, I think that's just business. I mean,
right. But does it have to? I mean, it's got to end at some point, right?
Yeah, I think that it's kind of ending in memory. If you know the players in like DRAM, there's only like a
There's 2 or 3, right?
Yeah, Hynix, Samsung,
Hynix,
Micron.
Samsung, and yep. And Micron almost bit the bucket a while back too.
Yeah,
so.
exactly. And
Yeah.
Wow.
they are working with, or they purchased Elpida or absorbed Elpida, which is from NEC and Hitachi, and there's a few others that. So it's I don't know how much more how much smaller the market can get or the players can get before there's issues with monopolies.
Well, actually, the players get bigger. There's just fewer of them.
You're right.
Yeah, exactly.
Yeah.
That's all too
that's
depressing. Funny. Can we have something more upbeat?
Yeah. So actually, I want to call out. So first off, your site is fantastic.
Oh, thank you.
Yeah, you've got a lot of great information there.
And it's HTML. Raw
it's
HTML.
It's Comic Sans. It's great.
It's funny you mentioned that.
Everyone off. Yeah, Comic Sans.
Everybody hates on Comic Sans, but I think it's fun.
And that's why I did it. And I'll tell you the other thing.
Yes.
And the other thing is, there was a book, I don't know, it's been a while now, that says, it was entitled Web Pages That Suck. And I used to tease my students. I said, my web pages are going to end up in this book, don't you? And they're like, really? You think so? And I'm like, yeah, I put it out there just to get the information out. And I use Comic Sans because everybody hates it.
That's great.
Nice, trolling the students.
Oh, yes.
Well, I wanted to call out the bad circuit design because not only there's a lot of good examples here. That was always my favorite part of art electronics too. Except you actually explain it versus the ones in art of electronics. I look at it, I'm like, well, what's wrong with that?
Yeah, right.
So thanks for at least explaining them. These are really good.
Oh,
so,
cool.
Yeah, these are.
I tried to put stuff in there that was useful. The examples from the book. So if you're trying to learn on your own, and speaking of layoffs, some of this went back to when there were really good people getting laid off, and they were like, well, I know this area really well, but I want to expand my knowledge. Can I take your class or whatever? And right in the mid 2000s, when we started having the economic problems, I taught in Boise on the cable TV, to broadcast so they could do the videos. Right at that point, they stopped doing the what's it called, the cable channel for the university. And so I bought this equipment and started recording the lectures, and people started using them. And then I started getting emails from people, wow, I studied your class, I did the problems, I was able to get a job. And then, it makes you feel good because, you're helping people and changing their lives. And so I've continued doing it. And the students now love it. And I always joke, well, do you guys really use the videos? Yes, we use the video. So
That's awesome. That's great. Yeah. Well, that's good. I think that we're gonna definitely look forward to the rest of when you get the rest of those courses out. I think that'll be really interesting, especially the real talk about op amps and everything. That's great.
Are they going to be free? Is it going to be publicly accessible?
Well, that's what I want. I already have on my website. If you hit the courses, if you go to look, I have taught Circuits 1, and it was in the summer, so it was accelerated, but I already have some basic classes. But I really think it's hard for students to stare at a lecture for an hour and 15 minutes on a computer. And so I'm going to try to break up the topics so they're easier to digest. I'm going to try to ask the university to make them public so that anybody can use them. The issue there is...
Because that's the way a lot of universities are going, the MIT open
Udacity
courseware and all that sort of stuff.
Yep.
MIT X. Yep.
So we'll see what happens. It's a new thing for me. So.
That's
well,
great.
it's a new thing for the universities too. I mean, they go, we're giving away all our lectures. Like, isn't that what people have been paying us hundreds of years for?
Yeah.
And
the answer is no. The answer is no.
Totally different paradigm.
The funny thing is, you get students that say, they'll send you emails, they want to go to grad school or whatever, and they'll say, I took the online MIT class and I know this subject. And then you talk to them and they don't know the subject because they didn't really enroll and they didn't have the pressure of doing the work and getting a grade and all that, So it's just, it's really a unique person that can be that self-motivated to really push themselves to learn from one of those classes.
Got it. All right,
awesome.
Jake.
Well, Jake, thank you very much. Thanks so much.
All right, thank you. Nice talking with you both.
Well, wait, where can people find, other than
yeah.
cmosedu.com, how can people find you online? Email, Twitter, or anything like that? Or?
No Facebook, no Twitter.
No Twitter. I can understand no Facebook, but come on, Twitter's the bomb.
Oh, okay. I don't.
No.
We'll get Jake signed up for Twitter just after this.
All right.
People can bug him on there. Hey, Jake, take a look at this circuit I just designed. What do you think of it? Yeah,
You're asking me to think? Don't do that.
Awesome. Well, thanks so much for being on the show. We really appreciate it.
All right. Thank you. Talk to you guys later.
Thanks, mate.
Bye-bye.
Catch you next time.